process conducted by Marcelo Fernando Condori Mendoza from Bolivia, who is currently working as university teacher at Universitat Provida France Tomao in the careers of system engineering and commercial engineering, as well as intern and volunteer at Society of Space Education Research and Development SSERD. So before we start the session, a few instructions to be given. Since this platform holds participants to 300, we will also be going live on YouTube SSERD channel, so you can suggest your friends to join over there. And to the right corner of your screen, there are two sections, chat and questions, where you can type down your questions and doubts related to the session, which will be taken by the end. And over to you, Marcelo.
All right. Thank you really much, Sneha. I really appreciate your presentation. Well, first of all, I want to thank the Society for Space Education, Research and Development for letting me participate in this event. It's such an honor. Today I'm going to address the topic regarding remote sensing satellites and optical image processing. So first, I am going to make a brief summary about some basic concepts we should understand. First of all, I'm going to ask the question, what is a satellite? This week, several talks are going to be focused on this topic. So it's important to understand the concept clearly. Well, actually, a satellite is associated with all artificial satellites which have been deployed and made for space engineering science. Among most important kinds of satellites, we can mention the Earth observation, communication, navigation, and weather satellites. We are also going to mention spacecraft which are intended for certain space missions. Today I'm going to talk more about the Earth observation satellites, which are also called remote sensing satellites. So let's describe some of the most important satellites we currently have for this purpose. One of the most important satellites today is Landsat. We currently have the version of Landsat 8 imagery, which provides high-resolution images. We should also describe some important agencies around the world. In case of India, we have the Indian Space Research Organization, right? And in South America, talking about the biggest country, which is Brazil, we can mention the Brazilian Space Agency. Agencies in different countries follow specific objectives for science and development. Not only about space exploration, but also about studying possible resources with observation satellites. So now let me ask you the question, what is the objective of remote sensing? Well, a general and specific concept relates remote sensing to collect information about an object without coming into physical contact. So basically it's like this. Let's imagine you are the person who are viewing through a microscope. In this case, what you are going to see into the microscope is going to be a small object. In that case, the Earth is going to be our small object. By taking to this scenario as a big scale, right, situation. So basically, remote sensing is like taking a big camera and taking pictures from several points outside the Earth. That's a general concept which I understand. The Earth has a translation and rotation movements, as we know. So depending on the engineering of satellites, satellites are going to swap in certain orbits, so they can take images from certain regions of the Earth. So that's going to be explained next. We should also mention the electromagnetic radiation, which is normally used as an information carrier in remote sensing. Talking about optical remote sensing is important to understand the principle of light. As a result, we will also describe what is radiance, what is reflectance, among other physical parameters. Well, talking about remote sensing, we can mention it developed through the first taking aerial photographs, like those one taken in 1839, right? Here we can see a picture from Circa in 1859, right? Taken by another. So basically, these kinds of work was very useful, and it would mark a new trend in taking pictures. We should also mention elements involved in remote sensing. First of all, we are going to talk about the illumination, which is the energy source. In this case, we are talking about the sun. And we will have radiation through the atmosphere, as we can see. So basically, the signal is going to travel from the sun until it reaches an object. That object is going to be the surface of the Earth, but the object could be a river, a mountain, one building, whatever kind of surface that the signal is interacting with. Next, we will have the sensor, right? So the energy is going to be recorded as information by the sensor. Next, once the sensor, as it is displayed in element D, once the sensor gets that information, it transmits that information to an antenna, right? So we have the transmission, reception, and processing. So that transponder in the Earth can send information to another satellite, or it can directly save all the information for later processing. So in F, we can understand the process of interpretation and analysis. And in G, which is the last write images, we are going to obtain our final result related to the application, right? That could be converted into a final product like a digital map. Now I'm going to talk a little bit about the electromagnetic spectrum. The electromagnetic spectrum takes into account the wavelength. So we can think like this. The longer the wavelength is, the higher the frequency, and vice versa. The lower well, in this case, the shortest the wavelength, and we are going to have the highest frequency, right? In this case, I am going to focus on the visible band, which takes into account three colors. We already know basic colors, which are blue, green, and red. And those are also associated with the bands I am going to display and process with the software today. So that's a main basic understanding of a small region of the spectrum, which is going to be analyzed. Well, we should also talk about what is spatial data, the attribute data, and the combination of spatial and attribute data. So that's going to differentiate among several GIS information systems, right? In this case, for example, we can appreciate the general representation of a map, like vectorial, right? So in this case, we are able to see roads and main streets from a city. So all those locations are represented through lines, and of course they have a georeferenciation, but this is more like vectors information. This information has already been processed, so the location is going to differentiate every location of elements in this image. Another important another important issue is regarding the main functionality of remote sensing. As I was explaining before, we are able to get information from images through the emission of energy. So that incoming energy comes from the sun. Once those signals, right, reach certain objects, some of this energy is going to be reflected. So that reflected information works as several signals. Basically, this signal is collected by the satellite, right? That's a main understanding about this mechanism. We should also talk about spatial resolution. Spatial resolution basically gives a certain quality of the image. The higher resolution we have, the best we can understand shapes, contours, and other important patterns in the picture, right, in the satellite image. But at the same time, the highest spatial resolution we get, or we have, in this case, is going to take highest amount of data, right? That's the main understanding. So we can see, for example, in the first image, a resolution of 0.5 by 0.5 meters. In this way, we are able to appreciate trees clearly and identify some construction houses and the main roads. There's not too much different when we see the right top image, right? With 2 by 2 meters resolution. But let's imagine like working in the 20 by 20 meters resolution, right? In that case, it's more difficult to differentiate between the houses, right? And also the vegetation. Maybe we can understand the vegetation, in this case, as a darker region, but it's very difficult to differentiate among main important patterns. So that might be a general overview of what space resolution is. So spatial resolution is going to be focused on the application we are analyzing. If we are analyzing, if the target is relatively small, of course we should get the highest resolution possible. But let's suppose our target analyzes were a very big region, like, I don't know, maybe a long region of the ocean. So in that case, we can take a lower resolution, lower spatial resolution, so we might be able to process images faster. I am going to talk now about some important remote sensing platforms. We can talk about Landsat series, which comes by Landsat 5, 7, and 8. There are also several other important satellites like Terra, Aqua, Sentinel from the European Space Agency is also very famous and very used nowadays. They have, for example, Sentinel-2A, Sentinel-2B. In the Sentinel-3A, they were able to implement several sensors like the SSERD, the OLCI, the RAL, the DORIS, etc. Right, and also sensors for global navigation systems. So it depends on the engineering, right, and the complexity of the satellite. So the payload can include several kinds of sensors. Talking about the image collection, it's important to realize the difference between polar orbit and stationary orbit. So many of remote sensing satellites available work in polar orbits. So some of them are intended and designed to cover specific regions from the Earth, right? So they are going to travel to certain locations in order to get information. We can talk about the geostationary orbit, which is going to have an orbit, in this case, parallel to the equator line, right? Those are most important differences. Now I'm going to talk about the concept of field of view. Field of view is basically an angle, right? So that angle is going to be designed according to swap region, right? In this case, the bigger the swap region is, the wider region we are going to take with the sensor. But when working in this in this projected area, there's also going to be an instant field of view. So that instant field of view is going to represent the spatial resolution on the ground, right? So as we can see in the right image, the smaller that angle is, the higher the resolution we are going to get, right? So that's going to depend on the main features from the sensor. Now I am going to differentiate between spatial and temporal resolution. We already understood what spatial resolution is. So the smaller the distance we can get, the higher the spatial resolution we get, right? For example, getting like 10 meters, 5 or 2 meter resolution in satellite imagery is such wonderful. But it's also important to understand what temporal resolution is. Temporal resolution is actually how many times during a certain period of time the satellite swaps over certain regions of the same target. For example, let's suppose we are saving information from one region in Nepal, for example. Let's suppose that the region, right, is remote sensed by the satellites every 3 days. So that means that the satellite passes over that regions this Wednesday, and it's going to pass over the same region in 3 days. So that would be Saturday, right? So that is the temporal resolution. So it's important to consider that depending the application we are working and analyzing, we are going to have more temporal resolution or more spatial resolution. It's practically impossible to have both of them, right, at the same time. That's because the satellites can move at a certain speed, right? And in order to get good quality images, the satellite wouldn't be able to pass through regions very fast. The engineering is specially established at a certain speed from the satellites, so they can cover specific targets, right? And also because commonly geostationary satellites um, have they complete one cycle the same period in which the Earth completes the cycle of 24 hours. That would be reflected that some certain satellites will only focus in one specific point of the Earth. So in this case, we can talk about, as you can see in the purple item, those are the emergency satellites. So, emergency applications like natural disasters, of course, requires both spatial resolution and temporal resolution, right? So, for example, let's suppose we are analyzing flooding, for example, in certain regions of, I don't know, Indonesia. So they require information as soon as possible, right? So if they get information every 2 days, right, maybe that's not enough. But if they at least get information every day, so that would be more productive and helpful. Let's talk about precision agriculture, right? So in that case, the highest the temporal resolution would be is like 1 month, right? For example, 1 month would be even too much for agriculture purposes. Maybe like 3 images per month, right? Or at least 2 images per month. So in this case, Landsat provides us information every 16 days. And in case of Sentinel-2, it has even a higher temporal resolution of 8 days. So let's talk about transport and infrastructure. In this case, the spatial resolution could be lower, right? And also, it's not necessary to have continuous images every certain period of time. So that's going to defense. So in the, well, then we can see topography, soil usage, forestry, geology, climatology, and time. So everything is going to depend on the specific objective we are working with. Now I'm going to talk about electromagnetic radiation, which is reflected in the analysis of three colors, red, green, and blue. Red works in 655 nanometers, while green color works at 560 nanometers. Finally, the blue color is reflected at 480 nanometers, right? So this is a schema of how colors are going to change according to certain wavelengths, right? Well, now I'm going to talk about radiance, what radiance is. Basically, the sun transmits energy, right? That energy is going to be explained by main traveling of a signal, in this case an electromagnetic signal. That electromagnetic signal is going to impact on the ground, and some of this energy is going to be reflected into the satellite. So that is how radiance is explained. So the most percentage or the higher amount of energy that the satellite can recover from initial radiance, the higher level of information about the soil or objects we are going to get. In this way, we can talk about three different characteristics or scenarios, like transmittance, in which signals, most of the signal continues their course, right? Continues the course of traveling, right? That is called transmittance. Absorbance, in the other case, is that the object or certain kind of soil has absorbed most of the energy. So very little or none of the energy is reflected back into the satellite. So finally, we can talk about reflectance, in which the higher percentage of the transmitted energy comes back to the satellite. So the signal travels in a certain angle through the zenith, and it goes back, right? So that's going to reflect certain level of reflectance. So those are the three main concepts analyzed. Now I am going to talk about the spectral signature. What the spectral signature is. We were able to understand reflectance already. So reflectance is going to be represented from 0 to 100%, or if you might think in another way, from 0 to 1, right? So in this case, we are analyzing the wavelength in nanometers, viewing the visible spectrum and also a higher spectrum, right? So the visible spectrum goes until we already reviewed it, goes approximately until 700 nanometers, right? Talking about the red, green, and blue bands. But we have also some other bands which are able to collect information which might be represented in colors also, right? That would be the infrared. There are certain small ranges from the microwave spectrum in which also colors can be captured. So this is the general idea of the reflectance diagram. So in this case, that green corresponds to forestry, right, to vegetation. So that vegetation is going to be reflected between 680 and 100, 1,100 nanometers, for example. We can appreciate that blue line corresponds to the ocean, right? To the ocean signature or to the water. So we can appreciate that most energy which gets in contact with water does not reflect the signal, right? The signal practically might be absorbed, right? Or it might be and the orange one corresponds to soil without vegetation, right? That could be rock, soil without vegetation, desert, and other groups of patterns related to this description. So it has a low medium reflectance, right? So in this case, we can understand that getting more information about vegetation or forestry in certain bands is widely available. Now I'm going to talk about image visual interpretation, talking about the wavelengths I already described before, 480, 560, and 655 nanometers. So talking about the red, green, and blue bands represent the real color. That's how we can see the natural vision, right? Of course, we are able to see more than three colors, but basically at images, hello, Kiru. Okay, thanks for clarification. I'm going to enable that again. Thanks a lot. All right, I guess. Well, I would like just to confirm if you are able to see the screen this time. Oh, thank you very much for the interruption. So maybe we didn't see the previous, right? We were talking about spectral signature from three different targets. Green one is forestry or vegetation. Orange one is related to soil without vegetation. And the blue one is related to ocean or water body. I was mentioning that the reflectance for forestry or vegetation is highly appreciated between 700 nanometers and 1100 nanometers. In case of soil spectral signature, we are going to appreciate certain regions of reflectance, which is between low and medium reflectance, right? And the lowest is for body. That's because signal is absorbed or transmitted in other cases, right? So very little of that energy, which interacts with water, comes back to the satellite. So that's the reason we have a very small value of reflectance. Well, this is the explanation when we are analyzing the visual spectrum, the visual region, in real color, right? Red, green, and blue. I was mentioning that the configuration of red, green, blue is the natural representation we can appreciate. But that's going to change, right? If we have very high resolution, we are going to distinguish among other colors in these three bands. But if we are working in a bigger area, or we are just covering more in this case, a higher region, we are just going to appreciate these three main colors, right? So there will be no, it will be difficult to differentiate intermediate colors between red and green, for example. So that depends on the resolution. So for example, this is satellite images in the red, green, blue band, which is visual interpretation real color. In this case, we can appreciate forestry, cultivation, we can differentiate construction houses, we can also differentiate among different kinds of water bodies, right? So this is the real color we appreciate. In this case, we are able to appreciate more colors, right, than just three colors. We can appreciate red or white, right, light blue, other colors, because this image has very high resolution. Now I'm going to talk about the infrared color. In case of infrared color, instead of working with the red band, we work with the infrared band, which is located at 865 nanometers, right? So of course the visual interpretation is going to differ because the colors are going to display differently, right? So this is the result of the combination of those three bands, right? So it's a little bit different. In this case, we can appreciate very dense forestry as red, right, or dark red, for example, right, while the cultivation soil is going to differ, right, among green or magenta colors. That's the main difference. We can also work with a compound false color. In case of compound false color, we are just keeping the blue band and the red works in the infrared, and we are moving the original green band to 1600 nanometers. So this is going to give us a very different result as we can appreciate in the image, right? So in this case, we can see like orange colors. We're able to see some blue, light blue, and cyan colors, right, for differentiating between other kinds of patterns for soil. So that is called a compound false color. So, well, basically, this is the main explanation I wanted to give you. So now we are going to work with the software system, so you are able to see how it works in a practical application. So now I'm going to share my main screen, and we are going to work with the software this time. So just give me some minutes. I'm going to reshare my screen, focusing in my main screen. So this is well, these are some of the images we are going to work with today. So we are going to follow the instructions described. So first, I am going to open the LC, the first satellite imager, right? So this is the software which is called Snap. Actually, I'm working with this version of Snap. This is the version I am using. So is Snap 7.0, right? It has these application tools, the Snap Desktop implementation version, the Snap Engine implementation version, right? Which are the most important ones. So this software system lets us work with optical and microwave satellite imagery. So I am working with this band first. I'm going to close this. So in order to display well, the colors of a band, you just open the products. I already opened the tree. So first I'm going to work with this one. So there are several options. You just right click and you might open the image window. So the most common feature is to open the red green band image window, right? If I execute this option, we are going to display three different colors, right? Instead of talking about colors, I am going to talk about bands now, right? Let's focus in talking about bands. So we can just work with three bands. There's no possibility to configure more than three bands. So the typical configuration is the natural color as red, green, blue. So that comes by default. In this case, we execute OK, and we are going to appreciate the image, right? So the main idea is this. The initial idea is to recognize certain target location in the imagery. In this case, since this image has a very good resolution, it's very easy to distinguish among this wide river, right? There's also the river, and this river which interconnects to urban cities, right? To cultivation with urban city. In this case, two different cities are being separated. So first, we would be able to differentiate among different targets. We are going to identify the Iguazu River, right? So I know which the Iguazu River is because this is located in South America. So we can work in this way. So I'm just going to select one pin placing tool. We are able to move the map through this hand, right? We just execute the hand and we are able to move the map according to our convenience. We are able to zoom in or zoom out, right? I think it's easier to do that with scroll, right? With scrolling mouse. So I am going to take about the pin placing tool to remark it, and I am going to call this the Iguazu River. This is the Iguazu River. So I can just name it. That's the Iguazu River. Now I would like to call the Parana River. But let's suppose that you do not know this region, right? Because it's easy for me to do this job because I already know this region. But let's suppose you are working in a region that you do not understand well. So an approach would be like working with Google Maps, right? To identify specifically locations, because in Google Maps you are going to be able to identify location, but maybe you are not going to identify the patterns of the surface, right? So in this case, I already moved into Ciudad del Este, right? And I'm already in the Iguazu River, right? This is the Iguazu River, as I already remarked, right? This is the Iguazu River. That's the Iguazu River. Now I want to identify the Parana River. So how can I know which is the Parana River? Maybe this is the one or this other one which is crossing through two different cities. So I can scroll on Google Maps and I already identified the Parana River, right? So this one is the Parana River. So I'm going to mark while the painting, right? So I mark this and I select the Parana River. So I can also change the color, maybe to differentiate. And I already know this is the Parana River. Perfect. The other one is going to be the Cataratas del Iguazu Airport. So maybe it comes an easy exercise to recognize airports easily. It's very simple to recognize because they represent just a very different color, right? Among the forestry. This is, for example, the airport. Actually, this is the main road from the airport, right? So I will just select the airport. In this case, I am talking about the Cataratas del Iguazu Airport. So I select a pin tool, right? I select. I will also change the color. And this is going to be Cataratas del Iguazu Airport. So I'll just rename it. Cataratas del Iguazu Airport. that would be a different color. Now I would also like to mention what the region is. We already understand this is a jungle, right? In this case, we can call it a forestry. But if I'm not sure, we can also review, right? We can also review the available image we have. In this case, it says National Park of Iguazu. So all of this is forestry, right? Forest or jungle, as you can, depending on in this case, of what kind of, of description you are more accustomed with. Most of the time we refer as jungles to forestry, but maybe in certain governments or other institutions, they will just call them a jungle, right? So I can call this like jungle, this lower region, right? So all of this is going to be like jungle. So I can just select a new point and rename it. I'm going to take green color. Yeah, I can take this one. Yeah, this one I can take. And I could call his name Iguazu Reserve. Iguazu Reserve. And there's another interesting water body, this region. This is also other kind of region. We know this is water, but this water body is different, this kind of river. And if we appreciate the Google map, we know this is called Embalse Uruguay. That's the name of it. So I'm going to name it that way. So I will just take this point and I will change it to yellow, and I will call it Embalse Uruguay. Okay, so that would be the initial, I will finally select one different city. We have two different cities here. This is one city, this is another one. One of those is called Ciudad del Este, as we can appreciate here. The region located in the left, right, in this case, in the east is Ciudad del Este. Right, that's called in Spanish, Ciudad del Este, right? The west, in this case, the east city, that's called. So I'm going to call it as Ciudad del Este. All of this is Ciudad del Este. So I can take a pinpoint. I will change the color to this, and I will call it Ciudad del Este. I think that's enough now. We can continue analyzing other patterns, right? But we have certain time to do this. So I think that's it for now. We can also take into account cultivation, I guess, but that's enough, I guess, by now. So those are the identification of regions. We can also measure distances, right? For example, if we go through the airport, we can measure, right, the distance of this airport. It's like just taking the measuring tool. We already understand how long this, right? So it's like 3 kilometers approximately, right? This road of the airport, right, to understand. And now we are well able to identify certain locations, right? Now, what I would like to do is to identify geographic coordinates. In this case, I'm trying to locate three different coordinates. One is, for example, Ciudad del Este, right? So if you want the approximate geographic coordinates of Ciudad del Este, maybe you can go downtown or to a middle point, right, like this one. And you can appreciate in the pixel information. So you just click this tab to just navigate to the map. For example, if you select this one, you are able to see latitude and longitude, right? So it's like 25 degrees latitude and 54 degrees longitude, right? That's the approximate location of the city. We can also locate Cataratas del Iguazu Airport, right? We were able to do it before. So these are the approximate coordinates, right? So that would be to represent or to save this information. And finally, crossing points between Parana and Iguazu rivers. We were able to identify both rivers, right? This is the Parana River, right? This is crossing two cities, and this is the Iguazu River. So the Iguazu River continues into this one, which is not so wide as the main reserve, but actually this is the crossing point of the two rivers, right? So this would be the exact location, the exact geographic coordinates would be described here. So that's also a general idea about locating geographic coordinates. What other exercises we can do? This is one kind of image. I'm going to open the other images now. So I will go again to the Product Explorer. I will also open this one. I will just right click, and I will also open with the RGB image window. I will select the default colors, which are red and blue. I will use. In this case, it mentioning green 432. That means red, green, blue. That's why it is called colors. So I will just keep this configuration. So those are three different images from the same location, right? So now I am going to display the three in just one window so I can differentiate between them. So I will just go to Window and apply tile horizontally, right? So when I apply this, I am able to see the three different images in just one window, right? So I can also zoom in or zoom out, right? So as we can appreciate, this first image has a very good resolution. This second one does not have a very high resolution, right? Because in this case, we can clearly identify this river. But in this map, it's going to be more difficult to differentiate between cities, right? Urban locations or cultivation regions, right? And also in this case, in order to identify Embalse Uruguay, it's going to be more difficult in the second image. How about the last image? It's also it also has very good resolution, right? The only difference with image is it does not cover the same region as these two, right? It's a little bit lower, I guess. Yeah. So the region is more extended in comparison to Sentinel, right? But maybe the resolution in Sentinel is as good as or a little bit better than the Landsat 8 imagery. So that's the main difference between imagery. So that's it. Now I'm going to also measure, right, the pixel of of each of these images. I'm going to begin with this one, right? So if I just zoom in, I can identify one pixel, right? This small square, as you can appreciate, is one pixel, right? This is one pixel. So I can understand the approximate resolution, in this case, the spatial resolution for this image. So if I just measure, right, I'm going to measure from here to here, and that's about 0.029 kilometers, right? So it's like talking about, you can understand, near 30 meters, right? It's something like near 30 meters approximately. So I think the resolution is good, but let's look at the second one image, right? The resolution is very low because the distance is quite much higher, right? So if I go to the second image and I apply the same exercise in order to see the resolution, right? I can also measure the distance between these 2 points, and that's about 0.479 kilometers. So that's almost 500 meters, right? So this is a low resolution image. So maybe this image is very helpful for analyzing forestry in big areas, but it's not going to be useful for analyzing, for planning, for urban planning, for example, right? And finally, this last image. This also has a very good resolution, right? If we compare the first with the last image, we find that the last image has a higher resolution, right? I can go through it and I can measure again. I can measure the distance, right? So it's about 0.0099, right? So that's almost near 10 meters of resolution. So definitely this third image is better for exploring purposes. For example, if we take, for example, a very big area, if our target is a very big area, in that case, the resolution among the first and the third image is not going to make the difference, right? If we check this whole area, there's no difference. Maybe we can think this is the first image, the landscape is a better approach. But let's suppose that your target area is smaller, right? Like just focusing on Ciudad del Este city, right? This one. So if we want to analyze this region, of course, the third image is going to be much better than the first one in this case. So as you can understand, the space resolution in this case is going to be a relative concept, right? So we cannot say that the highest resolution imagery is the best. We can just mention that it depends on the application we are trying to apply, right? So that's the main concept about this. So now we are going to continue doing some other exercises regarding bands, right? So in this case, I will just I will work with this image. I will just this last one, and I'm going to close, for example, this. And this, I'm going to work now with the Sentinel image because it has a wider resolution. So I'm going to work with it. That's the image I already have. But now I'm going to open the infrared band. So in order to do it, I am going to, again, right-click on the target. I am going to open the RGB image window. But this time I'm going to change the bands. We already know 432 for natural colors, but I'm going to work with the 8, the 4, and the 3 bands. So I'm going to change this by the number 8. This will be the 4, the 4th band. And this will be the 3rd band, right? So it says natural colors modified. It's already modified, right? That's why it's changing also the name. For 8, 4, and 3. So I execute this, right? So it opens that second image. That's one of the exercises. Now I am going to open the last one, which is also uses the near infrared band, but this is called analysis of sane vegetation. So for this case, I'm also going to open RGB image window, but the band configuration is going to be 8, 11, and 2. So in this case, I just select 8, right? 11, 8, 11, and 2, 8, 11, and 2, right? So I just opened that third image. Well, I have 3 different images now, right? So maybe I can tile them horizontally again. Yeah, that will be better. And I can make some, well, depending on the pattern I'm analyzing, right, I'm going to see certain difference. For example, let's go through the river, right? Let's go through the river, specifically to this part. For example, in order to differentiate water body of rivers, we are going to different colors, right? In the natural colors configuration, I appreciate the Parana River as light green. It's a near green color. In case of this configuration, this is the infrared, we're able to appreciate the water body as a light blue or kind of a cyan color, right? And in case of false compound color, we are able to identify the water body river as blue, right? So that's going to be the difference. So maybe analyzing, while analyzing water, in this case, this part of the river is differentiated just as dark blue. But about the infrared, which is the second image, it's changing the color to green, right? Kind of green. So it's working like with cyan, and in this case, one kind of green color. And in the natural band color configuration, we are able to see the light green, and this part of the river is displayed as gray, right? It has a different colors, right? So maybe for water analysis, these two may be better, right? That's an approach. How about vegetation? Let's talk about vegetation now. Well, vegetation in this case, as you can display here, it is just displayed as different tones of green, right? Different tones of green. But in the second one, we can appreciate among green and red, right? And other tones of red. So maybe this second configuration is also much helpful for forestation, right? For green areas. This also is good, right? It's changing the color, but it's also to analyze different kinds of forestry regions. So that might be the difference between those cases. And talking about the analysis of vegetation, which is this last image, right? Let us understood a different pattern, right? A different pattern for different patterns for our analysis. So let's go deeper into the city, right? Let's go, for example, to this part of the city, right? Let's suppose that the target this time is going to differentiate between main roads and streets in the city. So if we go to the image, in this case, maybe it's difficult to differentiate a specific color right here for just streets, because we already know the buildings are in white color. They are differentiating because the level of reflectance. But in this case, we can see different colors for the street. It's changing to gray, to green, right? It's not uniform. In this case, it's not also very clearly identifiable, like using kind of magenta and green colors in certain regions of the street, right? But maybe for this last case, it's better understood because we can appreciate many streets as in a blue color, right? It's like a more intense blue color. So maybe it's like that interpretation. So we can say that the false compound color is let us differentiate among certain features much better, like roads and streets, right? For example, in this case, it's difficult to understand the roads, right? Because maybe we would require a much higher resolution image to understand or analyze urban cities, right? Urban construction. So that's the main different analysis we can implement for certain bands. And now what I'm going to do is just to take into account certain regions we were previously analyzing, right? So I'm going to work here, and I'm going to recall in this case certain regions. For example, the natural reserve. We already know all of these is the natural reserve, right? So I'm going to here call a point, and this fourth point is going to be called the Iguazu Natural Reserve. Iguazu Natural Reserve. Kind of forestation, high forestation. And I will call this Ciudad del Este. Yeah, or if you want, you can call it, for example, urban city, urban construction, right? That would be called a pattern. What else? Let's analyze one final kind of feature, right? Here in this region, we can appreciate different kinds of cultivation. These are different kinds of cultivation. So the most predominant one is this, right? In this case, this kind of color, right? Like here. So it's going to have different zones. In this case, we have here, or we might even understand that region as soil without vegetation, right? Actually, this is the one with vegetation. So we can remark this, for example, this one. Let this one be the black, for example, and we are going to low vegetation soil. That would be. We know, for example, this has just more vegetation, right? Or maybe this one is like, this is cultivated region. So I'm going to change the color. It will be cultivated region. So I have already selected several patterns. So now I'm going to apply the spectral film. So once I have selected several patterns in my map, I'm going to go to the optical and select the spectrum view. Once I select the spectrum view, I'm going to show spectra for all pins, right? So in this image, we can appreciate the analysis we are following, right? So which has the higher one? The red one has the higher one. That is cultivated region, right? So that has a very high level of reflectance, right? This is the reflectance. Which has low, for example, the blue one, which are the rivers. We already know that water bodies do not reflect the energy. That's the reason. Other low, of course, is the Parana River, right, which is also low. A medium one would be this black one, right? What is the black one? The black one is the low vegetation soil, right? That has a medium, not very high reflectance level. How about this green one, this light green one? This light green one corresponds to the Iguazu Natural Reserve, right? Since there's plenty of vegetation, of course, it's going to reflect most of the energy. So this is the analysis we are following for for our main target, right? That's the main analysis. Well, so that would be then the initial analysis by now. So maybe what I can do, I still we still have some minutes. I would try doing some kind of exercise, right? Since we have analyzed all of this, I can try making one kind of small exercise if it's possible. Let's see. Okay, so let's work in this in this questionnaire. It's going to be, I think, productive and helpful, right? For example, the first question says to identify coverage in the next image, right? In this case, we have urban, we have water, we have cultivation, and we have natural vegetation. So as we can understand this region, for example, as you can appreciate, this is using the infrared band, so it's most closely related to this scenario, right? This is the band's configuration which is being applied. So as you can see in this case, construction regions are going to be like light blue, like cyan color, right? So we can understand that cyan configuration is urban, right? So that would be urban. What is going to be water? In this case, water, for example, is going to be this dark blue body, right? How we can understand that? Because part of the river, as we can appreciate in this here, part of the certain regions of the river are darker, right? As in this case, for example, this is dark. So in this case, this one also, right? This light dark region is also river, right? But here there's a bigger water body in this region, so maybe we can just follow this, right? That would be water. How about cultivation? We already know by the features that all of these are cultivation fields, right? So we can select among those ones. Like here, for example, natural vegetation, right? Finally, we are describing natural vegetation. Natural vegetation might be this one, right? Which is a little bit darker. That would be the visual interpretation we might apply. Right. That would be. So I can apply it to test the analysis. We can make it, maybe try and do another question. This is next color combination corresponds to an image in false compound color. That's false, right? Because we already reviewed the false compound colors, which takes into yellow and orange colors. So this is false because this is taking into account the infrared band, right? Instead of the red one. So this is false, right? And well, in this case, this is asking us about the spectral films. We can try answering these scenarios by the exercise we have already applied, right? So if I display again the spectrum view, right? Which had the highest, I think? The highest is the cultivation regions, right? Some of the cultivation regions might be the higher, right? In this case, this might be the highest, which is the green color in this case. Then, how about forestry? Well, forestry, in this case, we are going to review. Basically, are the artificial forestry we call, right? So the artificial forestry is a little bit lower, right, than the natural, right, the artificial. So this would be the blue one. And in the middle, we can see maybe this is the one in the middle, the jungle, the Paranaense jungle. We have cultivation, the jungle, and forestry. So we will see if that's true. What else? And it's asking about the reflectance value for a water body in the band of 665 nanometers. So we have that information already, right? We have two rivers. One of the rivers is the Iguazu and the other one is the Parana, right? So it's talking about the 665 nanometers band. So it's near here. So in this case, it's like this value approximate, right? It's like 0.075 value of reflectance. So that would be like 0.08. So that would be like 0.08 approximately. It's really low. That reflectance is really low. So let's see. Maybe this would change, right? Because analyzing the vegetation would make some error, right? Maybe this is going to differ. Let's see how we made this test. And we are sure about this one. Okay, let's finish this try. What it says. Well, in this case, three were correctly selected. Two were correctly selected. How about this case? This was even lower, right? We didn't appreciate where the value was. The value of reflectance was even lower. This was okay, and this was okay also. Well, so that's a general analysis. So now I'm going to reply some of the questions. So let me go back to the main permit. I think there are some, well, one of the question is which application is using now? Well, which application I'm using now? This is the software, the Snap software tool. So if I'm going to let you know. So this is Snap 7.0. So replying that first question, Snap 7.0 software. This is a free software from the European Space Agency. That's it. What else? What else? Which other question? Where can we download the Snap? They say. Okay. So, well, you just go to. You can look at the information like this. Download, for example, Snap software. You're going to find it easily. So to download, you just go to this web link. Here you can download the latest installers for Snap. So in this case, I'm going to copy this to the Hermit. That's for software downloading. And if you can appreciate, you have version for all kinds of operative systems. In this case, if you want to install the full tool or all tools, you just select this one, right? Windows 64 bits, and you just apply download here, and you will be able to install it. That's it. Other questions we have now. Let's see. Other questions. Okay, there's one question which says, in satellite camera cache and get damaged by orbits, then how we can find it? All right, well, basically all of this information is continuously monitored by technical staff. So when they download the images, they are able to display all the information. So basically what they do, for example, in every image, there's metadata, right? Here we can say metadata. So some information regarding the image is displayed, right? So in this case, we know the exact date, right? This, for example, is from January 5th, 2018, right? The image. It specifics well, it specified the specific time, the region of the target by location, right? Normally, it's going to be described by the resolution of the images. They are going to evaluate the quality of the images by comparing a series of images. So once they find the differences, they might be able to discern if the image is correct or not. There might be some errors also, right? For example, these are optical images. Since we are talking about a signal dispersion, we are talking about scattering. So if there's, for example, well, there's rain, there's cloudy season, right? Some of these image is going to be, some regions of the image are going to be white, right? That's how these optical images might be affected. So in this case, technical staff are going to pre-process images first. They might apply some filtering. Once they filter the images, they might upload the images. Or they will directly be able to understand, right, the quality of the images. So normally this satellite has, well, has a life of 7 to 9 years approximately. So they may expect, the technical staff might expect the images are well captured among a 7 to 9 year period. But let's suppose we are covering more than 9 years. We are in the 10th year of operation. So in that case, they will already understand that maybe the resolution is not going to be the best one, right? So they are going to monitor the quality of the images. And once they might not be able to upload this available imagery, maybe the satellite is still working, it's still going through its orbits and getting the satellite imagery, but maybe the quality is not good enough in order to be published, right? So that's going to depend on several factors. Also, they will be able to understand the main physical factors by telemetry, right? By knowing the exact amount of energy that the well, energy for all payload systems which is implemented. Well, there's one question regarding about the false color. Okay, what's the false color? This is the false color. Why is it called false color? Because it's using different colors as the natural or the infrared bands. Instead of using green or red for vegetation, it's using the orange, red colors. That's why it's called false color. Actually, false color is going to be reflected on the configuration which was applied, right? When I was opening the image, I just applied the different configuration, right? In this case, I was using different bands. In this case, only the blue band was kept. I changed those bands, right, previously. So that might be the main difference, like 11, the 8th, right, and the 11th band. And of course, there are several bands, so maybe you can test also other possible. Let's see, for example, we change, instead of using the first band with 11, we can use, well, with 8, we can use in this way 11, 8, 2. So let's see, right? So this is the final product we are able to see in window, check horizontally, right? I'm also going to close this one. I'm going to close the other ones. Yeah. We'll close these ones. For example, this is another configuration of the opens, right? So for example, this is also false color, but instead of using orange, we are able to display light green for forestry, right? Maybe for some people this is easier to understand, right? So basically that false color combination of bands is going to depend also in the experience of the remote sensing analyzed or the main purpose of targets specification. Well, I think that would be the whole presentation for today. I just presented some important concepts about optical image processing, the general concept of reflectance, and what are the spectrum, what are the spectral frames, and how we work with them. This is just some basic part of optical image processing. There's a lot to do, but of course we wouldn't be able to do that in 1 hour. It would require at least 4 hours in order to cover more practical material. So I don't know if there's any other question. I think we have already finished the presentation, which was planned for 1 hour today.
Thank you so much, Marcelo, for the interactive session.
Thank you very much, Sneha. I want to thank the SSERD for letting me participate once again.
Yeah, we are very glad for that. Thank you so much. And we end the session here.
All right. Thank you very much, Sneha. And I also wish all participants to continue attending. There are several interesting talks this week, and I think you are going to learn a lot, right? Especially if you are getting involved in this field of science for the first time. It's going to be an amazing, wonderful experience, I guess.